Hi. So, today we're going to be looking at a variety of proofs, and with the final so near and me being so brain dead, I already pre-wrote to make it more manageable and neat. And also, not too many jokes this time around. I think this is going to be a real serious video. Really want to emphasize that part. You hear that? So, for the first one, we're going to be looking at the arc length proof. And here we have our function and we have our arc length that I've really painstakingly highlighted. So this line DL, the small change in the arc length, is the tangent line. And typically the tangent line is going to be a lot closer, but then that'd be a real mess. So with that tangent line, I formed a triangle to represent the small change in x and the small change in y. And that is going to give me the Pythagorean theorem to use. So that's going to be dl squared equals dx squared plus dy squared. And to isolate dl squared, we're going to end up with dl equals the square root of dx squared plus dy squared. Now that's cool, but we have dl as a small change in the arc length, but we want the actual arc length itself. So we're going to take the integral and get L equals dx squared plus dy squared with the square root of over it. But the thing is that we don't know the values the integral is going to go from, because that is going to vary depending on situation to situation. Now, the two different situations we can have is whether the function is in terms of x or in terms of y. So for f of x, we're going to factor out the d of x from the whole equation, and we're going to end up with L equals the integral of 1 plus dy dx squared over square root dx. And because it's f of x, we're going to go from the x values of the function. So we're going to go from a to b. Now it's the opposite with the g of y. So the function is g of y. We're going to do L equal, we're going to factor out d of y, and we're going to do the arc length is equal to the integral of 1 plus dx dy squared square rooted dy. And the integral this time is going to go with the y values from c to d. Okay? Okay. Now for the second one, this is going to be the arc length of a polar curve. So it's similar but a little different. This time we're working with theta, and we're trying to find the angle. We're trying to find basically the length of between two angles. So because we're working in polar, we want to go to parametric to make it easier to work with. And we can do that using this little handy dandy conversion. Now it's r of theta, but to be simpler, I'm just going to write r. So we'll just disregard the theta a little bit. So we know from the last one that d of L is equal to the square root of dx squared plus dy squared, but this time we're working with theta, so we want to have that into the equation to make sure, and it's d of theta. So what I'm going to do now is I'm going to take the derivative of x equals r cosine and y equals r sine, and that's going to be using the product rule, and I'm going to end up with this just monstrosity. And if I work that out and simplify it even further, I get this, and minus 2r sine cosine dr d theta, and this 2r sine theta cosine theta dr d theta are going to cross out and simplify. So we're going to end up with dl equals the square root of r squared sine squared plus cosine squared plus dr d theta squared cosine squared plus sine squared, and both of these are going to simplify to 1. So we're just going to be left with dl equals the square root of r squared plus dr d theta squared. And if you take this integral of that, you end up with L equals theta 2, from theta 2 to theta 1, the square root of r squared plus dr d theta squared. That's the answer. Thank you. The sample problem for like an arc length. So something like, for example, from 0 to 1, we have f of x equated by 1 plus 6x to the third second power. This is our formula that we're going to use for the arc length. So you just have to find the derivative of 6x 3.5, because 1 is just going to be 0. Square that, and you're good to go. And that is going to give you the integral that you need to figure out what the arc length actually is. So for the area arc length of a polar curve, we have the equation r equals 6 sine theta from the range of 0 to pi over 2, designated by the formula length equals square root of r squared plus dr d theta squared. and that is going to give us with a derivative of 6 cosines theta. It's going to give us this integral right here, and that will present us with the arc length of a polar region. So for this last one, we're going to find prove the surface area for an x-axis rotation of an arc. So as you see here, we have a bit of a dip. So the closest thing to that is going to be something like a cone. So as we know previously from your video, begin. So what I want to go over is the area of a cone. As you can see here, we have our radius and our length. And when you take out a piece of it, you're going to have a 2 pi r for the length, and then on each side L. So to find the area, we're going to use 1/2 r squared theta. And when you do that, you're going to cancel out these L's and these 2's, and you're going to end up with an area of pi RL. Like I said before, when you do the bend, that is what gets you the 2 pi. So that's what the area of a cone is going to be 2 pi y dl. And we know that this little ring here, which is representative of a cone, is going to have a small change in the arc length, which is going to be dl, and the radius, which is going to be represented by y. So the area of all that is going to be 2 pi y dl. Hi, quick update here. So the reason why it's 2 pi y dl is because you go around like the cone band, and that little bend gives you the 2 pi. So that's where that comes from. I'm so tired. So cool, we have the area. So we have surface area being the integral of 2 pi y dl. And again, like with the arc lengths, there's going to be 2 different versions of that depending on the situation of the function. So for f of x, we're going to have the surface area being of 2 pi f of x, not y because we're in the x world, times the square root of 1 plus dy dx squared dx. And also from a to b because x. Yeah. And for this one, for the surface area for g of y, we're going to have 2 pi y to the square root of 1 plus dx dy squared dy. And we can keep the y because we're still in the y world, and y is going to go from c to d, the vertical, points. So if we were doing y-axis rotation, we can also prove that by doing the same process, just reverse. So for f of x, it's going to be surface area is the integral of b of a times 2 pi x times 1 plus dy dx square root squared dx. And for g of y, surface area is going to be the integral of d to c times 2 pi, not x, g of y, we're in the y world, so square root 1 plus dx dy squared. And yeah, that's it. Can you see it? Oh yeah, I forgot we had to do sample problems for these. So here's mine for the surface area. So we have the length of y equals tan x from 0 to pi over 4, rotate about the x-axis, as you can see from this awesome picture right here. And this is the formula you use for the arc length, and it's designated by the, here with the surface area formula, designated by the 2 pi y because we go around the x-axis, and the 2 pi comes from the bend. Like I said, probably before this. So you set up like that, and then you end up with 2 pi tan x to the square root of 1 plus secant 4x.